Okay. Hello everyone, I'm Lazare from Team Georgia, and today I'll present topic number 16, sinking bubbles. So when we oscillate the container vertically, bubbles can sink in the water instead of rising up. We have to investigate under which relevant parameters is this phenomenon observed. So at first, let me show you my experimental setup where I use a speaker as the oscillator of the container and take the video with camera, which takes 240 fps. We also control frequency and amplitude of source by computer, and we have firmly attached speaker and the container to test to avoid set of oscillations along x-axis to avoid experimental error. And finally, what we conclude from preliminary observation is that there is some critical depth when bubble begins to sink, and this critical depth is dependent on all of the relevant parameters which I've shown in the slide. Second, and this is the way bubbles sink in the water. So I will investigate it, but until then, this is how I'll be taking the data from the video analysis. So first, this is the demonstration of how bubbles sink in the water. This is the low resolution. This is the video by low resolution camera, but it's better to see because we see exact trajectory of the bubble. So we take this video and we cut it by frames, and if we want to observe only sinking, then we have to take this middle parameter and take this by the tracker. Okay, now let's talk about the explanation of phenomena. Until that, I have to explain what is the attached mass effect. Okay, when the object moves in a fluid, some amount of fluid has to move around the object in order to move. So if this object moves, it has some acceleration, then it means that water which would be accelerated around the bubble when it moves is called attached mass. And we could calculate it by Newton's second law and unsteady Bernoulli equation. And for spherical shaped bubbles, we have this kind of expression of what is the attached mass, how amount of more water will be accelerated while it's moving. Okay, now the main explanation of phenomenon is the question is how does it help actually bubble to sink? Okay, let's compare these two situations. The first one is when the bubble position is the upper position, and the pressure is lower, which means that its volume will be bigger, and the attached mass around it will be also bigger than the second position. Which means that when it goes up, it has to displace more water, which means more resistance when it goes up, and low resistance when it goes down because of the forced oscillation from the speaker. This is the exact reason why bubbles sink in the water. Okay, now let's talk about the theoretical model. So at first, from this we calculate the sum of every forces acting on the bubble, which here is just the regular mass cross acceleration part of the equation, and the first one is the attached mass component, which is dependent on volume and the time, of course. But another side of the equation, we also have the drag force, always opposite direction of the motion, gravitational force, and the buoyancy force. But acceleration here has two components, gravitational and oscillation components. But if we want to solve this equation, at first we have to investigate volume dependence on time, drag force, and amplitude of bubble separated. So let's move on with volume dependence on time. The only assumption is that the motion could be isothermal because we think that the heat flow from the air gas to the water, we think that it's quite high. That's why because of its property ratios, for example, volume of the bubble is much smaller than the containers, we think that this motion could be isothermal. So we use Clapeyron's law and describe pressure as the dependence on time with this two-component acceleration, and finally get how isothermal isothermally velocity is dependent on time. But we think that under high frequency and amplitude oscillations, when the oscillation happens in very short time, we think that the motion could be adiabatic because heat could not be transferred in such a short time. And we just use a work energy equation to estimate what under which omega, amplitude, and radius is motion adiabatic. And finally, just write the Clapeyron law and adiabatic equation, and also describe the pressure and time. And then under this after these boundary conditions, the motion becomes adiabatic. Okay, now let's move on to drag force. So we write this drag force for the spherical shaped objects, and the C coefficient is the drag coefficient, and this coefficient is quite important because This is dependent on Reynolds number, which actually defines is the flow around the bubble turbulent or laminar. So what does it change? If the flow is turbulent, then it means that it could qualitatively increase the drag force around the bubble because of the vortexes which could be observed under turbulent flows. And we take the the coefficient dependence on Reynolds number from the literature, and this is just experimental fitting, and experimental fitting. This is experimental formula. Okay, and now finally we could talk about the bubble amplitude and equilibrium position. Okay, at first in this slide we just use diode separation method, which means that we take the motion of the bubble and separate it into two parts, which is the sinking, the slow motion, and the oscillation part. And finally, we could get these two expressions. First, it describes the bubble amplitude dependence, well actually bubble amplitude, which is dependent on time. And second one is analytical solution of when bubble begins to sink and the critical depth, of course. Okay, so the amplitude of bubble, as we see here, it has this kind of form. The lower we have radius and higher we have amplitude of source, the lower we would have the critical depth, of course, and it would be easy for bubble to sink in the water. This is how we take the bubble amplitude experimentally. And bubble amplitude is one of the main part of the problem, because we think because the critical depth is dependent on it, and critical depth is the main parameter which defines bubble will sink or not. And as we see here, critical depth is dependent on frequency and amplitude of the source, and the higher we have amplitude and the frequency of the oscillation, the lower we would have the critical depth. And also it's dependent on the viscosity parameter, theta. If we want to compare our theoretical result to experiment, we have to separate critical depth dependence on frequency and critical depth dependence on amplitude of it. And the main conclusion is that critical depth is most sensitively dependent on frequency. Okay, and finally, when we solve the governing equation, we have this kind of solution. For example, this is the case when the bubble is upper than its critical depth and it rises up. But the most interesting situation is when, for example, bubble is at the same height, and the same height. But we also observed that after some time, this kind of equilibrium position could have this oscillation part, which we call it steady equilibrium position. But of course we observed the linear sinking of the bubble, but we also observed experimentally some kind of unsteady equilibrium position when at first bubbles are at the same height, but then it begins to sink in the water. Okay, now I have to talk about the boundary conditions. Of course, we have to take the critical depth equation, and we have to take this critical depth equation. And as we see, for different ratios of the critical depth and height, we have to take these two variables. Actually, they are the variables which is sinking dependent on. And as we see here, this is a plot for different ratios of the height and for the critical depth and the height. And of course, when ratio is 1, the bubble would never sink in the water. Okay, but we still saw some bubbles on this graph when they were on this plot, but they still were not observable. So this could be talked about in the extra tasks. For example, these are the dissemble of bubbles under high frequency oscillations, and also actual trajectory of the bubble, which is not, of course, exactly linear. Okay, which could be caused by shapeshifting. First, we write just sum of every forces acting on the bubble and compare it to surface tension. And of course, when this sum of every bubble would be more than surface tension, the bubble would be dissembled, of course. And we can't see it, but well, actually, we've been increasing the frequency and amplitude of bubble, and we've been observing under which radius where bubble disassembling. And this is a theoretical graph, and as we see, actually there are only 4 points, but it's caused because we can't conduct our experiment on very high frequency and amplitude oscillations. Okay, and second one is how spherical is bubble, because actually bond number is one of the main parameters which defines is bubble is spherical or not, and we are allowed to say that if it's lower than 1, then it could be spherical. But better approximation is the Morton number, because Morton number, if it is in this range, then we could say that this is or spherical or ellipsoidal. So if it's ellipsoidal, then we have to talk about its trajectory. So if it's ellipsoidal, then it might be oscillating, and direct force could have this direction, which means that where the direct force would be exact, this would be the exact trajectory of the motion of bubble, and this is why we see zigzag motion of the bubble. But what changes here is only component of the direct force, because if it moves on a different trajectory than the linear, then it means that the direct force could have different the component, and the theta is the parameter which we take from our experimental observations. And finally, I have to sum up everything. First, we talked about the theoretical model, the governing equation which I showed you at the beginning of my presentation. Also, volume dependence on time, and the most times I've been using the isothermal motion. Also, we talked about the direct force and equilibrium and amplitude of bubble and equilibrium position of it, and got very interesting results. For example, critical depth dependence on parameter, which is actually analytical solution of the part. And here we see how critical depth is dependent on most relevant parameters, amplitude and frequency of the oscillation. And this is different kinds of the sinking, which I also investigated theoretically and also experimentally, just linear rising, linear sinking, linear equilibrium position, but also unsteady and steady equilibrium positions. And we also have this kind of system when I talked about the boundary conditions. These are the points when they were observable. These are the points when the bubble sinking was not observable and they were under the boundary condition. But these are the points were not observable, but they were not observable because of bubble breakup. And when bubble breakup, of course, the attachment changes, which changes the whole concept of the problem. And the main conclusion is that sinking of bubble is observable, but under very specifically defined amplitude and frequency of oscillation. I want to thank these people who were helping me in Georgia, but who didn't come on the IYPT. And finally, thanks for your attention.
Okay, first I'd like to ask you, how do you measure the radius of the bubble?
Oh, well, yeah, from the video analysis.
Just take a picture and measure
Yeah.
on the picture? Well,
Yes.
have you considered a visual distortion?
Sorry?
Have you considered a visual distortion?
You mean error?
We don't do this later. And do you know the restrictions for added mass?
Restriction? What
For
do you mean
added
by-
mass. Under what condition can added mass be used?
Yeah, and the mass could be used when the object has an acceleration, as I talked about. Because when it has an acceleration, the attachment
we can
has
talk
the
about
additional
this
force on the bubble.
Can you explain simply why bubbles sink?
Yeah, I explained it because when it's in the upper position, it has more added mass, which means that it has more additional force from the water, which means bigger resistance when it goes out.
So we see in this, it's a symmetry vibration, but it causes an asymmetry force. Can I explain this?
Which asymmetry force?
So I mean, like the bubble sink, but it is a sine oscillation.
Sine oscillation. Yeah, it is approximation, but if you want to talk about non-sinusoidal oscillation, we could talk about it in discussion because I have
And
this
you
kind
have
of
observed that the bubbles sink in a sideway direction. So it does not sink like this, it sinks.
Yeah, I investigated the zigzag motion. This is what I've been talking about in the
No, I mean, like it does not it does not travels only along
Yes,
the
the
y-axis.
zigzag motion on the x-axis motion, right? The zigzag
Yeah.
motion of the bubble. Yeah, this is what I investigated, and I said that it was because of its shape.
Okay.
Okay.
And
Let me
have you considered other kinds of liquid?
other kind. Yes, I conducted experiment on the oil and also honey. But actually, the main
right.
difference.
Oh, thank you. And have you considered other kinds of oscillations, such as square or round?
Well, no, because I was only able to get only sinusoidal oscillations from the computer.
Okay.
But qualitatively I investigated, and I can show it to you my results.
Okay.
Okay, thank you very much.